And we'll go on now with Alexander Hock from Oxford, who will talk about non-perturbative results of a just-renormalisable model.
Yeah, thank you very much. Thank you very much to the organizers for inviting me. It's great to be back in Münster. I studied here, I did my PhD here, so I lived around 10 years here in Münster. And we have these two different workshops coming together today, and one part of my title is just-renormalisable, which is the critical dimension of a theory, or a theory in the critical dimension. And on the other hand, I want to explain you something about a model where we can compute some non-perturbative results. This was work of my PhD thesis I did here in Münster together with one of the organizers, Reimer and Harald Grosse. And this model I'm considering here is called the Grosse-Wulkenhaar model. And if I have enough time, I will also talk about work together with Johannes Thüring, the other organizer of the second conference, about this model from an Hopf-algebraic perspective. Okay, first of all, an overview. So I want to motivate at the beginning, what is the geometry behind this model. So we are working on a quantum field theory on a non-commutative space, which sounds at the beginning harder, but actually we can do more in certain limits. It is the phi to the 4 model in 4 dimensions, which breaks down to a matrix model. And then we have like a double expansion. On the one hand, we have the coupling constant lambda, and on the other hand, we have a large n expansion. And in this formal large n expansion, different sectors decouple, and we can compute exact results. And the leading order in n is the genus 0. And I want to show you the exact solution in the 4-dimensional Moyal space for this phi to the 4 model for the 2-point function. And at the end, I want to talk about renormalization in the sense of Hopf algebras. Okay, so why should we consider a non-commutative space? So quantum field theories uses this operator value distribution, which is smeared over some support. But if we take and quantum mechanics into account together, we know there should be some minimum length, some Planck scale, some Planck length, which is very short. But if you have a minimum length and you want to measure something in space, you can just measure it up to this length. So, and if we have quantization in space, or even quantization in quantum mechanics, we know, or if we have uncertainties, that the uncertainty relation holds, that we have some kind of uncertainty up to some h bar, and you have operators which do not commute. So now we have quantization in space itself. So we should also have operators for the spaces which do not commute. So we have these operators, and the easiest space we can imagine is called the Moyal space. So, and you have these two space-time directions, and they do not commute, and the deviation is, the commutation relation is I times V. And on this Moyal space, we want to construct a quantum field theory. And the easiest quantum field theory you can imagine is the phi to the 4. So I want to construct, or I want to think about the scalar quantum field theory in Euclidean space on this Moyal space. I write it down that this good. I have to push a little bit harder. So it's phi to the 4 in d dimension on the Moyal space, and this is the action functional. So we integrate over the d dimensions. Later we take 4 or 2 in some examples, and then we have here the usual Laplacian. We have an additional term which is of harmonic oscillator-like term. We have a mass term, we have this star product, which comes from this Moyal space, and the phi to the 4, where we have phi star, phi star, phi star to the 4. And so first of all, the star product is defined here. It has an explicit definition, it's not important, but it includes this matrix theta, which is defined here, which is a matrix which has next to diagonal entries, which are multiplied by this parameter V. So the battery is almost empty, but okay. So by this parameter V. And the important thing is the star product, if you take V equal to 0, it's just a pointwise local product. So it's a generalization in terms of this parameter V. And we add this harmonic oscillator term in the middle here, because if you add this term, it was shown that this model is renormalizable, which was worked by Reimer and Harald. And this is why we add this harmonic oscillator term. And in the limit V to 0, we see that the inverse of theta goes with something like 1 over V. So this harmonic oscillator term would vanish if you send V to 0. Okay, so this is what we want to start with. And the important thing is, so you have this Moyal product. So you have an algebra of Schwarz function together with this star product. So there's a vector space. You have a basis, this F and M, which is a matrix basis on this space. And so it's very explicit how these functions F and M look like. And if you look at the star product of F and N with FKL, it has a matrix multiplication, and it has also this property here, which is a trace-like property. And if you have any kind of function phi in C0, so on this RD space, you can expand it in the spaces F and M. And if you have real functions, this parameters phi and M are elements of a Hermitian matrix. And now we plug in this expansion of this field phi in this action functional on the previous slide. And what we end up is a model like this. So we have that our action functional can be rewritten in this coefficients of this expansion, and we end up in a matrix model. So we said, so above there's written omega is equal to 1, which is the self-dual point. And we did this expansion, and we end up in the matrix basis with coefficients phi and M. And we have here, so we have the En here at the beginning, which describes the eigenvalues or the spectrum of the Laplacian. And we have our interaction. I also introduce some renormalization parameters. So Z is the field renormalization, lambda bear is the coupling constant renormalization, and in the eigenvalues of the spectrum, there's also a mass renormalization. Okay, and from this theory of the Moyal space, how is the dimension incorporated? It's incorporated through the multiplicity of the eigenvalues of the Laplacian. So Rn is the multiplicity of the eigenvalues, and if they are all distinct, then we have a two-dimensional case. If the multiplicity increases linearly, we have a four-dimensional space. If it would increase quadratically, a six-dimensional space, and so on and so on. So at this point, we have somehow, this is like, you can think of maybe a regularization. At this point, we have like discrete coefficients. And at the end, we want to also do a continuum limit of this, because this eigenvalues here are discrete at the moment. And good. Yeah, an important fact is that the interaction here, due to the fact that we have this matrix multiplications, or you think of a trace of matrices, this expression, it has only cyclic symmetry. So we have cyclic symmetry, and usually in quantum field theory, we have pointwise interaction, and it's completely symmetric. And here we have just cyclic symmetry, which means we have a vertex from perturbation theory, a vertex coming from this interaction has cyclic symmetry, it has an orientation, and our Feynman graphs, perturbatively, would be ribbon graphs, so like not just a line, but a ribbon. And these objects have a natural embedding on Riemann surfaces, which gives you this genus or boundaries. So we have more structure on the graphs. And then we can construct a partition function. So we have 5 to the 4 matrix models in this sense. And now capital N is the size of the matrix, and we want to relate capital N to the non-commutativity of the underlying Moyal space. And the partition function is defined in this way, that we integrate over all Hermitian matrices. Now we have to regularize, so N is finite but very big. And the measure is about all Hermitian matrices. It's like a product of Lebesgue measures. It's completely well defined for finite N. And we take exponential of minus the action. And I want to talk today just about the 2-point function. And the 2-point function is defined in the following way, that we take the expectation value of phi pq, phi qp, divided by the partition function, and have to normalize by v. Okay, and this is for some technical thing for two different eigenvalues. Okay, let's do that. Then what you do if you do quantum field theory, for instance, there are something called the Dyson-Schwinger equations. I don't know how familiar people are here with Dyson-Schwinger equations. These are equations between correlation functions. We can do this here as well. So usually a Dyson-Schwinger equation, which comes from, easily speaking, integration by parts. But you have a 2-point function. So the Dyson-Schwinger equation from 2-point function depends on the 4-point function. The Dyson-Schwinger equation of the 4-point function depends on the 6-point function. So for phi to the 4, and so on. But what we can do here in this model is that we can have these 2 different expansions in n and lambda, and we can rewrite the 4-point. So first of all, we have this expansion in n, which decouples somehow the different 2-point function depending on the genus. And we can write the planar leading order 4-point function in terms of the 2-point function. Which means that we can write a Dyson-Schwinger equation for the 2-point function in leading order in n just through the 2-point function. We have a closed system of equations just for the 2-point function. Then in leading order in n, we can compute the 4-point function from the 2-point function, and so on and so on. From that, we can compute the next to leading order in n for the 2-point function, etc., etc. So we get a closed system of equations, and we want to do that, and then do a continuum limit to get back this Moyal space. And we are sending the size of the matrix, because we have this formal expansion in n, and this parameter v, which gives you the deformation of the underlying space, of this Moyal space, together with a constant ratio to infinity. So we are interested here in a limit where the deformation of this Moyal space is infinitely deformed. So the opposite limit, actually. This gives you a cutoff. Then you have to renormalize correctly to remove the cutoff. And if you do this continuum limit, you can speak at the end, instead of discrete functions, you will get smooth functions on R or R plus. So X and Y will get then the smooth parameter on R, so that you have a discretized Laplacian, and this limit send you all the eigenvalues together, so that you have a continuum spectrum of your Laplacian. But we start with something at the beginning. We had, after regularization, we had some discrete eigenvalues, and you send it to a continuum spectrum. Okay, we can do that. It's not important, but one can do that. And then in this matrix basis, this 2-point function, this equation for the 2-point function is of this form. So we have a 2-point function here multiplied by a 2-point function where we have to sum over one of the indices. And here you have this difference quotient, again with the sum. So this is the leading order 2-point function. Dyson-Schwinger equation. Then we can do this continuum limit I said, and then the sum converges to an integral. We have cutoff, and so on and so on. So you have this equation. Okay, and if you can solve this equation, let's say in 4 dimensions. So here you have to do, you have to insert d equals 4. So this goes like quadratically in t and so on. You have to choose your renormalization constants in a way that it converges, etc. You would have the 2-point function. And this is what we did. We solved this equation. So it's a integral, nonlinear integral equation. This is what we did. And yeah, this was my work with Reimer and Harald from 2019. And this red part here, this is the important thing somehow. This is the important thing. Assume we know the red part, then the rest of the equation would be something that's called a singular integral equation. So we have a function, this red part, whatever it is, times a function. So this red part depending on x, which is maybe a complicated function. So function r of x times this function is an integral over where you had x here divided by this t minus x. So actually you have to take here the Cauchy principal value, but okay. So with complex analysis, you know in general, if you have such type of integral equation where you know this function here, you can solve it. So there's like a solution theory, it's called Kalemann type integrals. You can solve this type of equation, but we don't know this red part. So the red part depends somehow on the rest. And what we did is having the right ansatz for the red part, which is now this part here, you can show that it satisfies this linear integral or this nonlinear integral equation. And how is this red part we had constructed? You need one function r, and this function r is defined in this way. So it's an implicit system of implicitly defined functions r and rho lambda. If this function r and rho lambda is defined in this way, and you plug it in here, and you plug it in the other equation, you see that it works out. And this is the solution. So, which is completely non-trivial, but it's quite interesting that your solution is given in terms of implicitly defined functions. And maybe I should comment a little bit on the structure. So we define the function r as an integral over some measure rho lambda divided by something, and rho lambda is equal to r to the d divided by 2 minus 1 again. So let's take the example d is equal to 2 dimensions. D divided by 2 minus 1 is 0, so rho lambda is just 1. It's the easiest example. If d is equal 4, we have here 1, so rho lambda is equal to r. This equation gives you, again, a linear integral equation, and so on. And you can do that, and for the 2-dimensional case, you find that r of z is given by a logarithm, which was before computed by Panzer and Vulkenhaar. And we found like this general result for any measure you can compute this solution. And the special example on the 4-dimensional Moyal space, this linear integral equation then is solved by this hypergeometric function, which is very interesting. So the coupling constant. So we have this hypergeometric functions. Maybe people work with some hypergeometric function or know that. And just look at this hypergeometric function. You see that the coefficients of the hypergeometric functions depend on alpha lambda and 1 minus alpha lambda, where alpha lambda is the arcsine of lambda pi divided by pi. So this means, first of all, that the convergent radius in the coupling constant lambda is 1 over pi. Second, if you want to look in the literature of the expansion of a hypergeometric function with respect to the coefficients, It's very complicated. So I actually don't know if there are like closed formulas for that can be done, but this is a very interesting way of writing something down. So you have this expansion, the coupling constant, which is somehow wrapped in the coefficients of a hypergeometric function, not in the argument, which is here, but in the coefficients. And also for finite n, which would be like the zero-dimensional case, we have also expressions, again, in terms of implicitly defined things. So I don't want to focus on that, but also there we can write something down explicitly. Yeah, we have a finite radius of convergence in lambda in all these cases. And so inserting this R function back in this nonlinear integral equation, we can, in principle, write down the whole two-point function, which has this form. I mean, we can do that. It's not important how it looks like, but we can do that. Importantly, if we would expand this planar genus 0 two-point function in this ribbon graphs, and if we want to compute this ribbon graphs, we can do that and expand the explicit two-point function. These two results obviously match. So it gives the result, the perturbative result, and the explicit result is an expansion in lambda, where the explicit result is quite complicated because of the hypergeometric function and so on.
It should just involve polylogarithm.
Yeah, we have just polylogarithms. Yeah, that's right. So this no, I mean, okay, good, sorry. Yeah, we have just polylogarithms. So in this model, so it's much easier here than in ordinary QFTs. That's right. And but there's another thing which is interesting, that this example here, this quantum field theory, it's the renormalon problem. So you can find so the renormalon problem, for those who don't know that, is a problem due to renormalization. So if you look at the subset of Feynman graphs and you go to large order and n, you see that maybe this subset diverges with n factorial. The same happens here, but you have like other Feynman diagrams with goes like with minus n factorial and decomposes exactly and cancels exactly this problem here. So there's a very, I mean, from quantum field theoretic perspective, it's very interesting that you have a lot of different things here. And I should also mention, we have here also the sunrise graph, which was also shown in the previous talk. And in 4 dimension, if you want to compute the sunrise graph, it's not trivial. So you really need BPHZ, what we also heard in previous talks, this forest formula of BPHZ to renormalize this, which is non-trivial. So you need all kinds of perturbatively, like the whole technique of renormalization to make graphs finite, UV finite. So, and what we are doing here, I mean, this is maybe the important thing. Why can we do that? Why can we have explicit results? Why have we a finite radius of convergence? So for the two-point function, the first graphs in the coupling constant are at lambda 0, it's a free propagator. Then at lambda to the 1, there's a tadpole graph. Then I showed you all the graphs for lambda squared and so on. So this is like here. And then if you look at the next to leading order in n, the first graph would start with lambda squared. At the second order or the fourth order, it would start at lambda to the 4 and so on and so on. So what we are doing is we can compute this whole expansion in the Feynman graph expansion. So this is like the planar case, genus 0. We can resum this blue thing. We can get then later maybe the 4-point function and maybe the genus 1, here this one. All of these blue strips have the same radius of convergence. But what we are usually doing in quantum field theory, we try to compute this direction. And if you want to compute this direction, so we want to compute this, all Feynman graphs of second order, all Feynman graphs of third order, all Feynman graphs of fourth order. If we try to do this here, also, it would be non-convergent in lambda, actually. So you should also encounter again the problem that the radius of convergence is actually 0. But we can split this problem here, and this is the nice thing what we are doing. And the whole renormalization is located here. This is the important thing. Then I want to talk a little bit about the spectral dimension. So an important byproduct was that these hypergeometric functions in 4 dimensions. So if you look asymptotically how it grows, this is a general theory of hypergeometric functions, goes with 1 over x to the a. And our function r, which was related to the effective spectrum of this theory, goes with x to the 1 minus alpha lambda, where alpha lambda depends on the coupling constant. And the dimension of the system is defined by d divided by 2 minus 1, which was also, I think, in the previous talk. And so this hypergeometric function gives you an effective way of computing an effective dimension of this theory. And you see that we have a dimension which is reduced by the coupling constant. So effectively, because we can resum all this at genus 0, we can resum this whole set of Feynman diagrams, and it gives you a dimension which is actually a little bit below 4 dimensions, effectively. And this is also why we can resum it, because assume we would have just 4 dimensions and you have this integral equation we started with at the beginning, and you insert here something which goes just linear, not linear minus this coupling constant part. Then actually this was, this function here, r tilde, would have not a global inverse, which we need for this theory. So this is something we need for this theory, that we need a global inverse of this function r. And we would have like an upper bound, which would go like with e to the 1 over the coupling constant. But we don't have that. So we have the inverse of this function r. We can write everything down due to this dimensional drop, or this effective dimensional drop of the dimension. So yeah, this function r has a global inverse. And I don't think you can access this from perturbation theory, this observation. Okay, how long do I have? 50 minutes. Okay, perfect. Now I want to talk a little bit about the perturbative renormalisation of this model. So I think now it starts what I want to do, what I'm doing with Johannes. So since we can resum at each genus this sector and the coupling constant lambda, does it mean that the perturbation theory is simpler? Does it mean that renormalization is simpler for this model? And it's actually not the case. I said that a little bit before, that if we look at the sunrise graph, we have perturbatively these overlapping divergences, and you need this whole BPHZ forest formula, the whole theory, to make it finite. So it's quite complicated. And it's known that this BPHZ forest formula, the BPHZ renormalization, is actually, or has actually, a Hopf-algebra structure. This was found by Kreimer, and he had some work together with Alan Connes about that. And how does the Hopf-algebraic structure of this model look like? So is it different? Is it a little bit different? Oh, well, what are the differences? And this is my work, what I'm doing with Johannes. And what Johannes proved in previous papers is he actually took more general graphs, not just this ribbon graphs, but something related to tensor models. And he proved that if you fix some external structure, let's say, and let G be the set of all connected 1pi ribbon graphs, in my setting here now, you look at the Q algebra generated by G, you get a Hopf algebra. So for other graphs than ordinary quantum field theoretical graphs, you can also have a Hopf algebra where the product of the algebra is the disjoint union, and the co-product of the co-algebra is given by subgraphs, which you then contract. So you take a graph, you look at the sunrise graph, and you look at this subgraph here, and you contract it, and you get this graph. So this gives you like the way of constructing the co-product, you have an antipode, you have a unit, a co-unit, etc., etc. So this was done by Johannes for more general graphs, and we want to apply it here for this model. And for this, you need a generating series of these graphs. So this is now a different notation coming from this Hopf-algebra, quantum field theory people. So we look at a generating series in of this graphs with the fixed external structure. It's called the residue, and you're interested in the coefficients and where the okay, this is different alpha now, which counts the number of loops. And then, for instance, for the 2-point function, which are now the 1pi graphs, not the other graphs we had before, but it's just a geometric series to relate them. So the 2-point function, and let's say the 1pi, 2-point, 1pi, and 4-point function, you can write them down. And you can write something called the combinatorial Dyson-Schwinger equations for them. So we can write then the 2-point function in terms of the 4-point function and the 2-point function. This is a different Dyson-Schwinger equation, really focusing on renormalization and this Hopf-algebra picture. And the 4.1pi would be given in terms of all primitive graphs, 4-point primitives graphs, where you have some additional operator B, which explains you how you insert subgraphs, and so on and so on. So I don't want to go into the details, but the important thing is that for the 4-point function in 4 dimension, we have infinitely many primitive graphs. So you have the whole complexity here. We can write like an example of a sequence of primitive graphs. A primitive graph is a graph which does not have any subdivergences. To write this type of combinatorial Dyson-Schwinger equations down, so it's very complicated, and you cannot access somehow analytic theory from this approach. This is somehow what our understanding is. So this operator B, it's defined here with some combinatorial. It's not important at all, but the important thing is that this somehow reflects the complexity of renormalization of this problem, of this model, and it has the same complexity as an ordinary quantum field theory. Yeah. So, and what are the observations now? We have this coupled system of combinatorial Dyson-Schwinger equations. We have infinitely many primitive 4-point graphs. This CN, okay, this is a typical thing in this Hopf-algebra quantum field theory business. The CNs, these coefficients here of this generating series, they give you Hopf subalgebra. And this operator B is also in our setting called the grafting operators. It satisfies the Hochschild 1 cycle property. The same works here also. This is what Johannes and I are at the moment proving. But the difference is that here some of the symmetry factors are a little bit different than in ordinary quantum field theory, but these are subtleties. And you can, and if you want to look at an algebra homomorphism from the space of the Feynman graphs to the Feynman amplitudes, this is what usually people are doing in the Hopf-algebra business. You have to consider all these complicated symmetry factors, and you can actually not do that in a very nice way. So actually, exact results are not really accessible with this Hopf-algebraic perspective from our point of view. And we are also doing it because in the past there was some Hopf-algebra analysis, Hopf-algebra structure analysis on the Kloster-Wolkenhaar model, which is, from our point of view, maybe not completely correct, and we want to correct it in the literature. Yeah, then let's summarize again what we can do in this interesting model. We have a non-commutative underlying geometry, which combines you somehow a little bit, maybe gravity and quantum field theory, and which gives you at the end a matrix models. And there's a lot of literature about matrix models, and you can do a lot of things with matrix models. And we are able to compute closed Dyson-Schwinger equations together with some Watt identities we had to use in the formal 1/n expansion. So this is very important here. And we are getting exact solution in lambda at each order in 1/n. In the 4-dimensional case, we have an effective drop of the spectral dimension of the spectrum of the Laplacian. And the resummation in N is not convergent. So we avoid this problem where you would actually need resurgence and so on and all this theory. We avoid this problem, but just concentrate on a formal expansion N, and we know that the whole renormalization is in the leading order in N included. And for fixed order and the coupling constant, so this was like this vertical, the red vertical in this picture I had, there are just finitely many terms at the fixed order in N, just finitely many Feynman graphs which contribute, and actually you can resum it. If you know this whole tower, you have just finitely many terms at each order in lambda to the n, but they increase like factorially. And yeah, this is also again what I mentioned a few times. So just the genus 0 sector, this first line, this first blue line, has to be renormalized. This is the important thing. We don't have renormalization or a new contribution at the next order and the next order in n. And genus 0 has, and for genus 0, we have the same complexity in renormalization as an ordinary quantum field theory has. So we have field renormalization, we have mass renormalization, we have all this renormalization constant to include. Also from the Hopf-algebraic perspective, it has the same complexity. This combinatorial Dyson-Schwinger equations are very complicated. There's one thing which we don't have, which is a running coupling. But I expect resumming 1 over n, which gives you like this finite radius of convergence, which should shrink to a radius of convergence, or to having radius of convergence 0, would maybe give a running coupling, but I'm not sure. Yeah, I'm maybe a little bit too fast. Yeah, I stop here. Thank you.